You're about to finish a long road trip when you pull up to a horse ranch and realize that's not the Grand Canyon. You're still about 300 miles away. Damn you, GPS! Hey there, little Kyle. It seems you're lost. What, because we can tell exactly how far away a star is that GPS should just work? Do you even know how we figure out distance in space when we actually can't reach anything? Yeah, I thought so. You know what? Seeing as your vacation is already ruined, why don't I show you the 7 levels of space distances? And yes, exactly how we measure just how far space objects really are. It involves crazy wild lasers, creepy undead stars, and even one of the most unique types of supernova in the universe. Oh, and of course, I'll show you what's the absolute farthest object we've measured so far before the absolute limit of what can be measured according to the laws of physics. Level 1. Yes, we don't even need to leave the desert for this level, because measuring all of space started right here on Earth. First, you need a ruler to measure stuff, right? Well, I was there 2,000 years ago, when a Greek named Eratosthenes measured how big our own planet is with just a stick and a shadow, and basically got it right. And once you know the size of the Earth, you can use the entire planet as a measuring stick to work out just how far away the other planets are, and from there, even the distance to the sun itself. That took us centuries, but now, we just skip the whole thing, fire a radio signal at a planet, wait for it to bounce back, and since we know exactly how fast light moves, that just gives us the distance. Yeah, in 1961, they aimed that same radio signal at Venus, and that single bounce finally locked down the most important number for measuring space distance, the astronomical unit, the true distance from the Earth to the Sun. Later finalized to exactly 149,597,870.7 kilometers. Before that, we knew the shape of the universe and that Jupiter sat about 5 times farther from the Sun than the Earth, but 5 times what though? Nobody could say. But after the AU was finalized, oh yes, now we could get busy measuring. Just like how Mongolian Horse is gonna get busy at this horse park. It's been ages since he was able to run around with his own kind. What's that? Oh, he says he hasn't had a date in decades. Weird flex, but okay. My favorite flex is that the Apollo crews left little mirrors sitting on the moon, and to this day we fire lasers at them and then time the light coming back, which is how we also know that the moon is drifting away from us at 3.8 centimeters a year. About the speed your fingernails grow. Cut those damn things, by the way. You're disgusting. And all while this makes sense, light spreads out and fades as it travels, right? So a radar beam fades extra because it has to make the trip back to Earth. Bounce one beam off Saturn and you're already struggling to get good signals. Aim past the solar system and there's simply nothing left out there to hit before it dies. So how exactly do we measure stuff at the edge of the solar system and beyond? And what space objects can we use to help us do exactly that? Level 2. Okay, so we can't bounce anything off of stars, but here's the amazing part, Kyle. We don't have to touch something to know how far away it is. We just have to look at it twice. And no, not like that time I ran into an anvil on my way to mail a birthday package to my dad. And certainly not like Mongolian Horse right now with 2 female horses next to him. No, hold your thumb up, Kyle, and close one eye, then the other. See how it jumps against the desert behind it? That jump is called parallax, and the closer something is, the bigger the jump. It's the exact reason that on your drive out here, the cactuses by the road went flying past, while the mountain on the horizon barely moved at all. For the stars beyond our reach, instead of the inch between your eyes, we use the biggest free ruler we own, the planet itself. We photograph a nearby star tonight, wait 6 months for the Earth to swing all the way to the other side of its orbit, a trip of about 300 million kilometers, and yes, that is why the astronomical unit mattered so much, because the distance is almost identical on the other side. Then we photograph the star again. Because it moved slightly, a little bit of math gives us the distance. The first time anyone managed it was in 1836, on a dim little star called 61 Cygni, about 11.5 light years away. The first distance ever measured to another star. But of course, they didn't use light years then. The original number just got so absurd that kilometers became pointless. So the science bros invented the light year, the distance light travels in a year, and the parsec, which is about 3.26 light years. Today, a satellite called Gaia runs this exact trick on nearly 2 billion stars at once. mapping a huge slice of the galaxy with frankly ridiculous precision. So while this parallax method is very limiting from Earth up to like 1,000 to 3,000 light years, Gaia can extend that to 30,000 light years. Imagine how many destinations we will map. We can plan vacations in the future as you age and die, and then I can put your brain in a weird tube so you'll always be alive with me as a robot. I will take you to see the stars, Kyle. However, for objects further out than this, the star just stops appearing to move. And that means we need new methods to find the distances of objects. But how accurate are they? And how can we use them to measure
the farthest galaxies in the history of the universe?
And how far is that? Level 3. Wait, Mongolian horse, what are you? Oh, he's saying he'll stay here and do the measurements while we can go quickly into space to see just what objects we'll need to do this. Excellent idea. Good thing my G-Wagon can also become a spaceship. Let's go. Okay, now that we're in space, Kyle, this is the exact moment things stop being honest. Everything up until now, we measured exactly, mostly. From here on, we're making educated guesses, and the whole thing kinda runs on brightness. Think about a candle. Held right in front of you, it's blinding, and perhaps burns off your massive eyebrows. But far enough away, it looks tiny. So if you know how bright something truly is, like exactly, how dim it looks tells you exactly how far away it is from a simple formula we can use. The problem, you have to already know the true brightness, and for most stars, we don't. We just see a dot, but some stars are actually kinda easy to literally measure. See, back in 1908, an astronomer named Henrietta Leavitt, who was barely paid and watched men slap their names on her work, classic holes, noticed a special kind of star that physically pulses, swelling brighter and dimmer like it's breathing. And the slower it breathes, the brighter it truly is. She timed the pulse, and the star just gives you its real brightness for free. Well, it costs math. These are called Seyfert variables. They are very rare yellow supergiants that are tens of thousands of times brighter than the sun. They're in an unstable phase where a helium layer traps heat, then releases it, making them physically swell and shrink in a steady, reliable rhythm. Just like my beats when I DJ at the seniors' home on Sunday afternoons. And this happens over days to months, making them easy to measure. Yes, these are the very first space measuring sticks, and they are called standard candles. And they've got an older, dimmer cousin called RR Lyrae that do the same trick. An amazing discovery! Just like that radium is radioactive. I actually found that out myself when I was drinking those sodas that literally had radium in the ingredients. I died. Good thing my mother quickly brought me back home and used string therapy. Anyway, in the 1920s, Edwin Hubble found one of these pulsing stars inside the fuzzy cloud in our Milky Way called Andromeda. He timed it and realized it sat like 1,000,000 light years away, too distant to live inside our galaxy. Andromeda wasn't a cloud at all. It was an entire other galaxy. And that's how we know there are other galaxies. Literally. Before that, the Milky Way was thought to be the only one. Amazing! But as great as these Seyferts are, like a candle being too far away, they too have limitations. It's at this point we need something far brighter and far more violent. A dying star. Level 4. Well, fortunately, the universe has a genuinely deranged star waiting for us, Kyle. Meet this perfectly ordinary white dwarf. The dead core left behind when a sun-like star burns out and sheds its outer layers. Go on, fall onto it! See? It's a corpse! Earth-sized, but so dense a single teaspoon of it would weigh several tons. So how the hell is this a supernova that we can use to measure the universe when white dwarfs exist because the star didn't go supernova? Normally, all these little guys would just sit there and cool forever. But sometimes a white dwarf has a living companion star right beside it. And that's when it stops being dead and starts being undead. Ah, those damn witches and their spell. Every time I say undead, that happens. Oh, how does it become undead? Simple, because the white dwarf begins stealing gas. Like that time I stole all of your string cheese and bacon while you were sleeping on the couch. See, the white dwarf is so dense that it starts siphoning gas off its neighbor into an accretion disk, then piling onto its surface and fattening it up, heavier and heavier. Sadly, there is an absolute limit ruled by the laws of physics for how massive a white dwarf can be. 1.4 times the mass of the sun. The instant it crosses that line, a white dwarf can't hold itself together anymore. Its dense material ignites all at once, and the star literally detonates in a thermonuclear blast briefly as bright as a whole galaxy. Yes, literally. That, my dear viewers, is a Type 1a supernova. Almost as bright as all of you beautiful people that subscribe. Of course, Type 1a supernova also happen when white dwarfs merge with each other. As long as that mass limit is reached and exceeded, stuff will go boom. And yes, these Type 1a supernova all blow up at the exact same mass limit. As soon as they cross 1.4 solar masses, they all explode with almost exactly the same true brightness. Look at these light curves that show the light. Yes, see? That makes them the perfect long-range candle because we detected some nearby galaxies that also happen to have Cepheids. That means we let the Cepheids tell us the real brightness of the supernova, and suddenly we're measuring distances billions of light years out, halfway across the visible universe. But even a dying star this bright eventually fades into the distance. So what do we do when we can't make out a single Cepheid or catch a supernova? Because that's a real problem, by the way, like trying to find the McRib or the toilet after you've had milk that's gone bad. Hold on, the phone's ringing. Yes? Yes, Mongolian horse, I know! He says we have to measure a whole galaxy at once. Level 5. Right, so when a galaxy is too far to pick out a single Cepheid and no supernova is conveniently exploding, how the hell do astrophysicists measure a whole galaxy, and how does that even give us the distance? Well, there are a few clever ways to do it. 1. Every red giant hits the same peak brightness the moment its core ignites helium. None can shine past it. So when you look at all the brightest red giants in a galaxy, they all have the same approximate brightness. Done! 2. When a spiral galaxy rotates faster, it gets brighter. So scientists measure the spiral galaxy spin and calculate its real brightness. But how do we know that? Because first we calculated the spin and brightness of galaxies that have Cepheids and supernova. Now, for those that don't, we can simply compare the rotation to the ones we know. Amazing again! 3. And this might sound like a bit of a joke, Kyle, but we can literally measure a galaxy's graininess. Just like your pores. Get a facial, by the way. My girlfriend took me for one and my skin just opened up. What's that? My whole face is a blackhead? Listen here, you little I'll make you a lump right here. Just like how up close a galaxy's light looks lumpy, you know, star by star, and far away it smooths out into a haze. This texture alone gives the distance away. Each method suits a different galaxy, all calibrated by the Cepheid variables and the Type 1a supernova. But notice what's happening, Kyle. Every time we try to measure objects further out, we're trusting more and more relative to those two objects and directly measuring less. And to reach the truly distant universe and measure the farthest galaxies of all, even a whole galaxy isn't enough. We need the one thing left: photons themselves. Level 6. Everyone knows space itself expands. So while a galaxy's light spends billions of years crossing it, the light wave stretches right along with the growing space and therefore appears red. That's redshift. And here's why it gives us the distance. The farther a galaxy is, the more space sits between us. So the more stretching stacks up, which means the distant galaxies are fleeing faster away and their light is shifted redder. We measure this shift exactly. Every element glows at fixed known wavelengths, a barcode printed onto the light basically. We find that same barcode in a galaxy's spectrum, measure how much it's been redshifted, and that tells us how fast it's moving away based upon the rate of expansion of the universe, calibrated naturally by the Type 1a supernova we already trust. Oh, trusted white dwarfs, we thank you. Also, they're a cereal in the 11th dimension. I had them as a kid every morning, but we didn't use milk because otherwise, how could you see them? No, we mixed it with blue tachyon milk. Well, I wasn't meant to tell you that those are real, so let's move on. Okay, so that all sounds good, but this is where your brain might leak out of your ears. Whenever you hear that such and such object is 13 billion light years away in galaxy such and such, it's not actually 13 billion light years away. That's just how long the light traveled to get to Earth. While it was doing that, space kept stretching, so that galaxy is now sitting around 33 billion light years away. And when the light first left, it was far closer, like maybe only a few billion light years away. How far is it? Suddenly is 3 different correct answers. Yes, Mongolian horse, again, if you want to just... Oh, there he is. What do you want to say? Right. He says that this redshift is still the tool we use to measure the distance to the most distant galaxies that have ever existed. So, what is the farthest we've ever measured? And is there a limit beyond which we can never truly observe? Level 7. So, here it is, ladies and boys. The farthest thing we've ever measured is a baby galaxy, MON Z14, existing just 280 million light years after the Big Bang, 13.5 billion years of travel. But the real answer to your question is a bit more spooky. Yes, there is a limit to how far back we'll ever be able to see. Space is expanding faster and faster, so everything past a certain line is being dragged away from us quicker than light can actually cross, which means the light will never reach us, and no future telescope will ever change that. Physics has blocked off most of the early universe, forever. But for measuring distances in the universe, every level we just discussed leans on the method below it. So when we measure how fast the universe expands two different ways, they always disagree, and nobody knows why. Which leaves us somewhere deeply uncomfortable, Kyle. Either one of the 7 levels we just climbed has a flaw hiding inside of it that we can't find, or physics itself is keeping a secret from us, and there's no way to tell which. The most precise map of the universe ever built might also be wrong? True! At least supervoids will probably expand and kill us all first. Maybe.